Hello and welcome to today's session. We're looking at the ideal gas law, and we need to be able to use the gas laws and the ideal gas law equation. So the assumptions for the ideal gas law follow on from the laws of the gases that we've seen so far. So Boyle's law, Charles' law, and the pressure law. Remembering them, so the particles are moving randomly, they don't attract each other, they've got a negligible volume, the collisions are elastic, and there's very short duration of collisions. So that spells rave. That's a way to memorize some of the assumptions, because sometimes you're asked to specify some of the assumptions used for the ideal gas law, and when we come on to kinetic theory as well. Okay, so if we're eventually going to get to the ideal gas law equation, we also need to include Avogadros constant. That states that 1 mole of any gas contains the same number of particles. That's called Avogadros constant, and it has the symbol N subscript A, and it has a value of 6.02 times 10 to the 23 particles per mole. This is where there'll be overlap between physics and chemistry, because in these ideal gas equations, or using the gas laws, we'll be using moles. We've already defined temperature in terms of Kelvin, so we'll be doing that. And we've looked at absolute zero as well. So there's quite a lot of crossover between chemistry and physics at this point. We can find the number of moles of a sample by using the following relationship, where little n is the number of moles, big N is the number of particles, and Na is Avogadro's constant. So as a reference, we say in 1 mole of carbon-12, there are 6.02 times 10 to the 23 atoms. We can also find the number of moles of a sample if we have the mass of the substance and the molar mass. So we can use the relationship here. So mass of the substance divided by molar mass, and that will give us the number of moles of the substance as well. Thinking more about Avogadro's law with this Avogadro's constant, it is useful for ideal gases because the ideal gas constant is the same value for all gases. So that means that the volume is proportion to the number of moles, and that's constant for all ideal gases. Getting to the ideal gas law equation, from what you can see on the slide here, we've put down Boyle's law, Charles' law, and Avogadro's law, and we combine these three laws together and introduce a constant, because there's a constant for proportionality. If we want to turn that into a formula, we get the ideal gas law equation, which is PV equals nRT. So you don't need to be able to derive the equation, but it's useful to just know where it comes from. So Boyle's law, Charles' law, Avogadro's law, combining the three together and then introducing a constant of proportionality gives us the ideal gas law equation. The equation PV equals nRT is on your formula sheet, so you don't need to memorize it. So we can look at the ideal gas law equation, and we can write it in two ways if we think about a situation. So you could have a situation where there's changing states. So a situation where pressure 1, there's pressure 1, pressure 2, the ideal gas law can be written in terms of the number of molecules. So we've seen that it's stated as PV equals nRT. Using the relationship from earlier in the presentation, the number of moles is equal to the number of particles divided by Avogadros constant, and introducing another constant, which is the Boltzmann constant, which is equal to the gas constant divided by Avogadros constant. If we substitute that into PV equals nRT, we get another way to write it, which is PV equals nKT, where K is the Boltzmann constant and N is the number of molecules. This is on your formula sheet, so PV equals nRT and PV equals nKT are both on your formula sheet. Okay, so we've got the ideal gas equation and we want to use it for this particular example. So the question is, calculate the mass of oxygen in a tank if the pressure is 4.0 times 10 to the 5 newtons per meter squared, or we can say pascals, and the volume is 0.2 meters cubed, and the temperature is 20 degrees C. 1 mole, the mass of 1 mole is given as 32 grams. So we need to have temperature in Kelvin. So we need to convert that into Kelvin. So we can do that by adding 273. That will get our temperature into Kelvin. So first of all, we'll write down what we know. I've highlighted the key points. So pressure we have as 4.0 times 10 to the 5. Temperature, we need that in Kelvin. So 293. Volume is 0.2. We're going to use the gas constant R because we're going to use PV equals nRT. So that's 8.31 joules per mole per Kelvin. So we want to find the mass. So it's in two parts really. If we find the number of moles, then we can find the mass of the sample of gas. So if we find the number of moles, we can find the mass by multiplying the number of moles by the mass of 1 mole. So PV equals nRT. We need to make N the subject. So N is equal to PV over RT. Then substitute values in. Put that into your calculator. So a value for N, I get 32.86 moles. So we'll leave it unrounded at this point. Now we want to find the mass. So we want to find the mass of oxygen in the tank. So the mass is going to be equal to, we've got 32.86 moles. So 32.86 moles times 32 grams will give us the mass. So 32.86 moles times 32. That gives us 1051.52 grams. We want this in kilograms, and then we want it to two significant figures. So it's two significant figures, and in kilograms we get 1.1 kilogram. The ideal gas equation, PV equals nRT, gives us the possible combinations of pressure, volume, and temperature for n moles of ideal gas. So when we come to looking at questions, we can find the physical combinations, so the different combinations of P, V, and T. So either in this form, with N being the number of moles, or PV equals N KT. So we use this equation to look at the different possible combinations for ideal gases.